Hello everyone. Welcome back to week 2 of the course Introduction to Quantum Computing, Quantum Algorithms and Qiskit. In today's session, we are going to learn about how to program actual quantum computers using Qiskit. In the last session, we have learned how to program quantum computers using a graphical user interface called Circuit Composer. And in the last week, we learned basics of quantum computing. So we have tried to use these basics of quantum computing, these quantum computing principles, different single qubit gates and multiple qubit gates, and used all that information to build in quantum circuits on Circuit Composer. Today, we'll try to see how to replicate those kind of circuits on Qiskit. Today's session would basically have two parts. The first is a general overview of what is Qiskit, why is it important, what makes it a key differentiator as a software versus other counterparts, and what are the different self-learning resources. And all of this is available in the same platform, the IBM Quantum Experience, which we logged into last time. You can just go to your browser and type in quantum-computing.ibm.com. And the way you signed in for the Circuit Composer session, you can use in your Gmail ID or Facebook or Twitter or LinkedIn, or even if you have an IBM ID, and sign in there. Last time we had seen there were two buttons on your dashboard. One was launching Circuit Composer, the other was launching Quantum Lab. Today we are going to focus on the Quantum Lab part of it. That's where Qiskit resides. And then we are going to go deep dive into actual programming, wherein the first code that we'll do will be on entanglement. In our Circuit Composer session, we had 4 experiments. We learned how to implement single qubit gates, how to implement multiple qubit gates, how to put a qubit into a superposition state, and how to entangle 2 qubits. Today we are going to start from the 4th experiment, which would be entanglement. So our 5th experiment would be entanglement, but we'll see how to recreate that circuit using Qiskit. And in Circuit Composer, there were buttons on the UI where we could go set up and run, select whichever IBM hardware has the least amount of Q, or the simulator which we wanted to perform, fix in the number of shots or the number of times we wanted the circuits to run on the computer. And then we used to set it up and run. We used to go to our Composer jobs and view the jobs and do fine-grained analysis on the job and the job responses. Now we are going to see how to do all of this from Qiskit, and then we are going to also deep dive into visualization of Qiskit. Visualization of block sphere and Q sphere using Qiskit. In our theory classes, we have learned about block sphere, whereas in the last session of Circuit Composer, I showed you guys the Q sphere. Today, we are going to see which of them are useful for what purposes and when to use them. Finally, we'll move on to our first protocol, and I'll explain what is quantum protocol, quantum teleportation, why is it an important protocol, and then we are going to demonstrate quantum teleportation. So Qiskit stands for Quantum Information Science Kit. It's an open source SDK with a huge population of people working on it and contributing to it. The GitHub repositories are all available, and it helps us work with quantum computers at the level of pulses, circuits, and application modules. Qiskit is agnostic to the underlying hardware architecture. By hardware architecture, what I mean is the quantum computers that are programmed using quantum circuits are called gate-based quantum computers. And such computers or such systems can be constructed out of any quantum technology that allows defining qubit elements and can implement single or multiple qubit gate operations with high fidelity. At present, there are several such architectures which are based out of semiconducting semiconducting quantum dots or superconducting circuits, as in IBM's focus is into superconducting circuits. There are companies who are working on using trapped ions or photons and neutral atoms. And several of these are getting actively developed, and some of them are available to users over the internet. Qiskit is agnostic to such hardware design or such hardware architecture and can compile a quantum circuit to match the entangling gate topology of a quantum device, map the circuit instructions into the native gate set of the device, optimize the resulting quantum circuit for enhanced fidelity. The second most important thing is, as you guys know and you have learned in week 1, the amplitude and phase of a qubit are continuous degrees of freedoms, and they cannot be, or you cannot do operations on these accurately or exactly. Right? So these gate errors and along with the noise in which a quantum computer resides can ruin in a computation if not accounted for in the compilation process. It also may need additional mitigation procedure in order to obtain high fidelity output on present day quantum systems, which are called the noisy intermediate scale quantum computers, or the NISQ era quantum computers. Now, Qiskit is capable of taking into account a wide range of calibration metrics in its compilation strategy. It can choose an optimal set of qubits in which to run a given quantum circuit. In addition to that, Qiskit holds a collection of noise mitigation techniques for extracting a faithful representation of a quantum circuit's output. So this makes Qiskit a very big differentiator from all other tools out there which are getting developed yet. Qiskit has 4 main elements. The core component, which is called Qiskit, and previously it was referred to as the Tera, is the code foundation for composing programs at the circuit or pulse level. On top of it, we have 3 different components. One is the simulator. It's called the Qiskit simulator. It is used for accelerating development via simulators, emulators, and debuggers. Then we come to the Qiskit experiments, which we use for addressing noise and errors. And then is the application layer, or the Qiskit application module, which we use to build algorithms and applications. There are a lot of self-learning resources, and I've given pointers to some of them here. And the first one, and of course the best one, is the Qiskit textbook. It's an open source textbook. It's not just a course supplement. It's an excellent interactive book. With every concept, you have the Jupyter notebooks right in there, so you can directly try while reading the book and get a visualization, or get to see the outputs of what each of the operators, each of the gates, or each of the concepts actually mean. So that's a very good way of reading. Another interesting thing is that this book is continuously being developed, in the sense any new novel algorithm that gets published into a journal or a conference or a Nature paper, the entire material of the code is written in Qiskit, and then it is made easier to digest and in the form of a tutorial, and is added to this Qiskit textbook. So there are very interesting tutorials in the field of quantum machine learning, quantum optimization, and then applications in terms of quantum finance, quantum chemistry, and so on. There's a very popular Qiskit YouTube channel, and there are several other series within the channel. There are Coding with Qiskit series, wherein people come in and show how to program quantum computers using Qiskit. They are very short videos and very interesting ones, discussing a lot of these newer algorithms as well as the old quantum algorithms. There is Qiskit Live, which live streams all the public lecture series. Regularly, they have people from academia and different industries come in who are quantum experts, and they deliver their live talks. Then there is a superposition series, which explores how individuals can become Qiskit developers. And also there are 1-minute Qiskit, which are very short, FAQ type videos that always help, people developing or people working on Qiskit. Of course, there's Qiskit.org, where there is a lot of documentation, tutorials, and all of this present. And all of these resources and their links are present in IBM Quantum Experience, which we'll now log in and go through. Let's now go back to our quantum experience, and as you guys remember, this was our dashboard where we last time were focusing on this particular tab when we launched Composer. Again, today we are going to launch Quantum Lab, and the rest of the things we are very well aware of from our last session when we learned the Circuit Composer. So as soon as we launch lab here, people who have been working on Jupyter notebooks or on Python, you will see the layout of this dashboard is very, very similar to what you guys have been used to. On the left, you see all the codes that you have been working on, and on the right, you see these code snippets coming up. And notice that whenever you hit on a new file, this particular cell is an auto-generated cell. It has a certain amount of Qiskit libraries that are already included and some other imports. Then the next steps is what you can just continue doing and continue running. So we'll start with experiment 5, which is again going to be entanglement, but we will want to see how can we replicate the circuit that we built in quantum circuits using Circuit Composer, and that's exactly what we are trying to do here. So after having the standard import libraries, we are going to load in our IBM account. So once you have your provider equal to IBM load account, then this provider has access to what are the different types of hardwares that you have access to, and you might have more access than only the open systems. So this is important step to do. And now let's try to define our quantum circuit. So we'll define a value of or in a variable QC, we'll call and create a quantum circuit. So let's call and create a quantum circuit with 2 qubits and 2 classical registers. And as you guys might remember from our Circuit Composer tutorial, so the first thing to do is to set our qubit 0 into superposition. And how do we set our qubit 0 into superposition? We apply a Hadamard gate on it. So I write qc.h on 0, which is h at Hadamard applied on the 0th qubit. And then the next step was to apply a C0 gate. And C0 gate can be applied as .cx. So I say qc.cx. And then I of course have to mention the source and the target. Here I'm saying that the source should be the qubit at 0 and the target should be q1. Now we want this circuit to be measured. So we want to put in 2 measurements. So we want to measure, and of course we want to measure it on our classical register. So we'll have to give the mapping of which qubit is getting mapped to which classical register. So we'll say map each qubit to the respective classical bits. So Q0 and Q1 to C0 and C1. And then let us just try to draw this circuit. So we'll say qc.draw, and let's run this portion to just see whether I'm sorry, there is a typing error. So let's just rerun that. And that's exactly the circuit that we created using Circuit Composer. So we have a Hadamard applied on Q0, which sets Q0 into superposition, and then we entangle Q0 and Q1, and then we drag and drop 2 measurements, and we measure Q0 and Q1. Now the next step is to set it up and run on a Circuit Composer. So let's see how we can do that here. So first what we do is we call for a backend. So we are calling air. So air is for the simulator. So if we ask air, we are going to ask air get me the backend, and I'm going to mention any simulator here. Since we used custom simulators in our Circuit Composer code, so we are going to use the custom simulator here as our backend. So I've requested for a backend from air, and then I declare a few variables. So I ask to give it a job simulator chance to execute this quantum circuit QC on the backend that I have requested with a given number of shots. And now this number of shots, since we had 1024, the default number of shots in Quantum Circuit Composer, I'm going to use the same number of shots here. So let me just try to execute till here. Okay, I see an error there in name execute not defined. So let us try to solve that. And once this job gets executed, we want to have the results back in a results underscore simulator variable where we ask our job underscore simulator to provide us the result. So we call a dot result file on our job simulator. And then once we have our result simulator, we can just print the counts. So first, to get the counts, we say counts equal to results underscore simulator, and dot get counts is the function that gets us the counts or the probabilities, and we have to pass it the quantum circuit. So we want to pass it this quantum circuit and see how many counts we have. Let's also print the counts in here. These are the actual number of counts out of the 1024 times. How many times do you see? Oh, it should be count, and you see that it is in the state 11508 times and in the state 00516 times. And you might argue that this is not an exact 50-50%, but let's try to see it as a histogram. So in order to bring in or show a histogram, what we need to do is we need to say from Qiskit.visualization, I want to import plot histogram. And here I want to plot the histogram with the counts that I just obtained. The variable is count. So let's just plot an histogram. So we see that 504, this is at a 50.4% and this is a 49.6%, a close to 50-50 chances of being in the state of 0 and being in the state of 1. So whenever we see Q0 to be in the state of 0, Q1 is also in the state of 0 versus whenever Q0 is in the state of 1, Q1 is also in the state of 1. That is entanglement. Now, we saw these results in our circuit composer as well, and this is how we actually can run it in a simulator. Let's now try to see how can we run it in an actual hardware. So provider gets us the actual hardwares versus air gets us the simulator. So what we say is, what are the different backends? Provider can you show me what are the different backends that are available to me? So provider is going to show me that, okay, you have a couple of simulators. You have custom simulator, you have different backends. You have IBM X2, which is the Yorktown machine that we used in our circuit composer. We also used IBM Bellem in our some of our circuit composer experiments, and these are the simulators that you have access to. Now, what we do is I'll just directly go ahead and I'll show you two ways of doing. So in this particular code, let's directly say that, okay, I know the kind of machine that I want to run my codes on, and I just directly call for that. So I ask with the same command, get backend, but this time I ask to provider, not to air. Last time for simulator, I had asked to air. So now I say provider.get backend, and then I can actually mention the particular name of the machine that I am looking at. So I'm looking at IBM Bellem, which is here, and it's available. So I say, okay, give me the backend, which is IBM Bellem. And again, the same lines I'll have to do. So I can just go up in here, and I can just copy this sentence for the job simulator. The next sentence, as you guys know, once you have executed the results, you need to have the results back into a variable from which you can directly get your counts. So we take in the same variable here, and then let's try to print our counts. And let's try to see whether what kind of differences. So if you remember, we saw some differences in the simulator versus our no backend match. Okay, so let me just these are typos when you actually type in the code. Let us see. We should write IBM Q. The name here, if you see in the backend, is IBM Q underscore Telem. And as expected, it would take some time. There might have been Q on this machine, and we don't even know what was the result of the Q versus N circuit composer. We were actually going to the machine while we were setting it up, and we could see how many Qs are there, how many pending jobs are there. So this is definitely not the most efficient way of getting results in here. But there is an alternate way where you can get the least busy backend at IBM and run the circuit there. To do that, we'll actually try that as well, but in a separate code, not in this code right here. And I'll show you what is the syntax to do that. But for now, I'll just copy paste the lines till the code gets executed. So I'll take in the same visualization importing code, and I'll take in the plot histogram of count. And I'll also run it and we'll just wait. So we got the results back. And if you see here, 46% of the time you see Q0 and Q1 to be in the state 0, 0, and 48% of the time you see Q0 and Q1 to be in the state 1, 1. But you do see a very small insignificant, I mean, it's not really significant, but a very small number, where these many number of times out of the 1024 experiments that you did observe a result where Q0 was in 0 and Q1 was in 1, and Q0 was in 1 and Q1 was in 0. So this is not the state where there was a perfect entanglement, and that accounts for the gate errors and the noise in the qubit itself. So now once we know this is the way to write codes, and this is the way to actually run a circuit on an IBM computer, we'll go to the next modules, and we'll just try to do a couple of more experiments to see what are the other things that we can do on Qiskit, and what are the other small circuits that we can build upon. Next, let's try to do an experiment. It would be our experiment 6. So let's try to click on a new file and create an experiment 6. You can go to this new file. I didn't save the previous file. You can go to the 3 dots and then click on the 3 dots. You can rename this file and you can call it experiment 6 blocksphere versus Qisphere. Now again, as you see, when we start, there is an import auto-generated import cell that is created. So we can go here and then we can go to these 3 dots. We click on rename, and let's rename it to, you can call it experiment 6, and you can call it visualizations. Just to save space. And now it's loading the visualization.ipython notebook, and you see the first few lines are here. So we just execute this first few lines, and then what we intend to do in this exercise is we want to see what is the difference between blocksphere and Qisphere. So let's first try to load in our blocksphere and Qisphere. We also need to load in our command called execute. So we can directly write in here, or even here we can include execute. So from Qiskit we needed to import execute, and we'll rerun this line again. Let us also get from Qiskit dot visualization. We want to import specifically the Qisphere. So we want to plot state Qisphere. Again, the same things we want to do. We want to call out to Qiskit dot visualization and say import the plotting function for blocksphere. So it would go to plot block multivector. Now, once we have imported all the libraries that we are going to need for this experiment, we are going to create a very simple quantum circuit this time. And let's restrict ourselves to creating a quantum circuit of 1 qubit only. And we'll slowly proceed if we need more. But this time we are going to get the state vector simulator backend. Now I'm trying to divide your attention to back to the composer or the circuit composer session. And in the circuit composer session, we had been using the Qasm simulator all the time. Now the Qasm simulator returns us only counts, and we wanted to see probabilities or the number of times it is in this state or in that state, and that's why we depended on the Qasm simulator. Whereas now we're wanting to obtain the state information about the circuit once it has completed. So we'll try to get the state vector simulator. So let's first run the circuit, and then let's call for the state vector simulator. So we call the state vector simulator, and who do we ask it from? We ask it from air. So air get backend, and then we ask it to give me the state vector simulator. Now once I have requested for a state vector simulator, I can just directly run the circuit, so you guys know how to do that. So all you need to do is execute the circuit which you called QC on the state vector simulator, and you want to store the results in .result. So let's just try to run till here. And the state vector simulator, there is an E missing in this. So let's just try to rerun it. And it works. And once you have it executed, now you want to get back the results. So you call this state vector results as a variable, and then you say, I want the result dot get state vector. You pass it the quantum circuit on which you want to get the state vector results. And then now let's try to plot it onto the different visualizations that we have. So first we'll start with the block multivector. Now since you guys have studied about block sphere in your first week theory classes, let's see if it looks exactly like what you expected. So I missed another E here. Let's try to rerun this. And you get a block sphere. So you get a block sphere which starts from the center of the sphere, lies on the equator, and it points straight up to the North Pole, which is the state 0. Now that's what we expected. So we wanted to pass it, and we see that okay, we get a 0 state. Now let's try to display the state vector results on the quantum sphere. All you need to do is you say plot state Q sphere, and then again you pass on the state vector results. Let's run it and just try to see the difference. So we see that this is again the Q sphere. Now this Q sphere includes the phase information, as I pointed out to you in the circuit composer, that there is a difference between block sphere and Q sphere, and I preferred Q sphere there, as Q sphere includes the phase information of the state vector represented by this color coded little legend out here. So you see a red here because this is in phase, this is the phase angle of 0 radians. Now we might want to do some changes into this particular circuit, and let's try to give it a couple of twists. So what we did earlier, and let's try to flip this vector which is at its initial state of 0 to 1. And in circuit composer we saw that how do you flip the state of 0 to 1? You use a NOT gate or a poly X gate. A poly X gate implementation here means a dot X and the number of qubit on which you want the gate to be implemented. So here it's the 0th qubit, or it's just one single qubit circuit. So you directly you can just directly run it, and this is done. Now again you want to execute, so you can just go up, get these results. So you want to execute it on the same state vector simulator, so you don't need the simulator anymore. Just get these result line, copy it, type in back it here. And you not only need the results, but you also want this to be stored in some line, and then you want to plot the block sphere and the Q sphere. So let's just first see the block sphere, and then we'll also run the Q sphere. So now you see that in the block sphere, this particular vector has had a rotation, and it's now pointing to 1. So we have been able to flip its state from 0 to 1. And what happens if we plot the Q sphere? So now let's go back to the Q sphere plotting sentence. We'll copy this line in here, and then let's try to rerun it again. And do you see a difference? So you do see that this particular vector moved from 0 to 1 counterclockwise direction, and you still see the phase is 0 because there's no phase change yet. Now let's try to change its phase. So we are in the state 1 and the phase is still 0. Now let's place this qubit to superposition. And you know how to place a qubit to superposition. All you need to do is add a Hadamard gate to the 0th qubit. Now again the same line. So you have your Hadamard gate applied. You can just go into here, execute the circuit, and get the results and plot the results in a block sphere. So all the circuit lines are right here, all the codes are here, which I'm just copying and pasting and rerunning. Now let's see what happens to the vector. Now the vector you see is a state vector, and it's a precise combination, it's a linear combination of 0 and 1. So that's what you see here, right? So it is very different from what you had earlier. Now you want to really test the Q sphere again with every block sphere result. So let's copy the plotting of Q sphere in here, and let's try to run it. So now you see a difference, right? So let's just try to compare this particular block sphere with this particular block sphere. Now wait, there is a confusion. You see one single vector here. That's a 1 qubit circuit, but you see 2 vectors here. And this might be confusing, but not to worry. Just focus on the size of the circle, and that would give you an estimate of why you see this difference. Now, this small circle, this has a visual representation of the amplitude of each possible state. So when this amplitude was in this particular state, so it was only here. So this amplitude was purely one state. It was either a 1 or a 0 in the previous Q-sphere diagram, right? So versus now what you have is a linear combination. So you have the amplitude is not in purely in one state, but it is equally divided between the state 0 and the state 1. So that's why you see 2 vectors pointing to 2 ends. And here what you learn is a qubit can now, you can see that it can represent itself as a bit by using the basis states 0 and 1 that we saw here, the state 1 or the state 0 here. But it is also possible to be represented as a linear combination of basis states, that is 0 and 1, which is called the longitudinal one, and the phase shifts, which are the latitudinal one. Right, so there you see the phase difference. You see this is out of phase with pi radians, and this is in phase with 0 radians. So this experiment gives us a way more detailed understanding of Q-sphere versus block sphere, and why we see a lot more of information in Q-sphere, and that's the reason for using Q-sphere in the visualizations of Circuit Composer as well.